Okay, ladies and gentlemen. Unfortunately today I am out sick because one of you got me sick. I'm gonna guess it was Kirill. Um, or maybe Bad Stoyan. Anyway, one of you got me sick, so I'm out. But every day that I don't teach you and we don't make progress is a day less of you for you to be able to review for mock exams. So we're going to continue on. This is going to be comfortable. You'll be fine. You're just going to have to pick up the work from my class when you come in and take the high frequency, low stakes quiz. So we're going to look at a branch of discrete random variables and probability distributions called the binomial distribution. The thing with the binomial distribution is we have a number of trials, and when we talk about a number of trials, we're always going to call that our n. So the example I'm going to do, I'm going to have n is going to be 4 for us as we do this. And then there's only two possible results for each trial: success or failure. Now, and every time. So what I'm doing here, I'm going to use my baseball team, and for the first time in my entire career of teaching this to students, I can actually report that my team won more than it lost last year. And you can see here that the win probability for the relative frequency for the Tigers last year was 0.537. So we won a little bit more than 50% of our games, and we lost those. Notice that if I call this my P, then this, my losing, is 1 minus P, and that's actually how I calculated it because they report win percentage, never losing percentage. So if we just think about this for a second, if the Tigers would have won 3 of their last 4 games at the end of the season, they would have had a higher seeding in playoffs, and it would have probably made a difference for how far we got this last season. So I just want to think about the different ways that we could figure out the probability of the Tigers winning 3 of their last 4 games. So again, n is 4. So one way would be for them to lose their first game and then win, which would be 0.463 times 0.537 times 0.537 times 0.537. Agreed, that was one way for them to win. And I guess I could have abbreviated that just by writing 0.463 times 0.537 to the third power. All right, another way the Tigers could have done this would have been win the first one, lose, then win, and win. Well, judging on probability and the fact that you're in HL math, you're probably going to recognize that that's the same probability as this. That is because there's 1 loss and then there's 3 wins. And again, another way that this could have happened would be 2 wins, a loss, and then another win. And again, that's just 0.463 times 0.537 cubed. And then the last one would be win the first 3, lose the last, and I'm left with 0.463 times 0.537 cubed. So overall, the chances of this happening, or the way that we could figure out, is there's 4 different ways for the Tigers to have won their last 3 games. And that would look something like that. Now, I could continue to do this, and I could figure out, like, what was the chance that they win all of their games? Well, there's only one way for that to happen, and that'd be win, 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 win. which would just be 1, 0.537 to the fourth power. Similarly, losing all of their games would be 1 times 0.463 to the fourth power. Win 2, lose 2 there would be 6 different ways of them doing that, right? Think about it for a second. Win 2, lose 2. If you win the first 2, lose the last 2. Win, loss, win, loss. Win, loss, loss, win. Loss, win, win, loss. Loss, loss, win, win. And which one am I missing? Oh. Loss, win, loss, win. And so there's 6 different ways for that to happen. So that'd be 6 times 0.537 squared times 0.463 squared. And then losing 3 of the games would give me 4, 0.537 squared times 0.463 to the third power. Now, hopefully, you are noticing something about these combinations. And I'm going to give you a hint. This is a binomial theorem situation. The binomial distribution follows the binomial theorem. And now for some reason I can't zoom out. If you think about it, everything that I've shown here, what this actually is 1, so this is me winning every time, would be 0.537 to the fourth. And then winning 3 times, 4 times 0.537 to the third, 0.463. And then 6, split the 2 things. We're going to make this work, don't you worry. Maybe I won't, because it is not cooperating at all. And then this would be plus 4, 0.537, 0.463 cubed, and then 0.463 to the fourth. So what this is showing is that there's one way that they could have won all of their last 4. There's one way that they could have lost all of their last 4. There's 4 different ways that could happen. This is a binomial expansion. Out of curiosity, what do you think all of this has to add to? Hopefully you said 1. So if I wanted to know the probability that my team won 3 of their last 4, I would just have to calculate this right here. I'm just going to go ahead and do that. So that was 4 times 0.56537 to the third times 0.463. So my team had a 28.7% chance of winning 3 of its last 4. I guess that makes a little bit of sense, because if you think I'm winning 53% of the time as I play, so it would make sense that my team could have done that. So what this all leads to is anytime we have an event that is binomial, it either goes one way or the other, we can use binomial theorem. And we can use the binomial theorem with probability. What it's always going to be, I don't want that marker. What we're always going to work with is the idea of n, choose r, and then it's going to be the probability of the event that we want to the rth term times 1 minus the probability of the event that we don't want to happen to the n minus r. That is the binomial distribution. That will find the chances of something happening. Now, I have it formalized down here where you can see all of that. I just want to look at something else. I looked it up just before we started, and if my team would have won 94 games out of the 161 that they play in baseball. So there's 161 games. If they would win 94, they would have had first seed in the playoffs, probably would have done much better. So what I want to know is the probability that my team wins 94. So 94 would have put me over the top. So that would be 161, choose 94, 0.537 to the 94th, and 0.463 be 71, 67. Is that out? 50, yeah. So, I'm not going to do this by hand. I am lazy enough. So NCR 161, 94, and I'm going to multiply that by 0.537 to the 94th power, and then times 0.463, right? To the, and 161 minus 94, just so I don't screw it up. So what this is saying is that there is a 3.12% chance that my team, based on this, would win exactly 94 games. I am finding a particular value. If I wanted to find, and I can actually show you that in another way. So if we go menu, and we go to probability, and we go to distributions, you will notice this idea here, binomial PDF. That's going to find a particular value. So the number of tries, there's 161 games. The probability of success is 0.537. And I want to know, to win 94 games, what it would be. And if I do that, you'll see it's the exact same value. Your calculator is a godsend for this. Now, if I wanted to know what is the probability that X is greater than or equal to 94, well then I would have to take this and I'd have to add the probability of winning 95 games, and then I'd have to add the probability, I'm not going to write it all out, of winning 96, and I'd have to keep adding those values together. And we call that a cumulative density function. So finding that value, we would add all those together. But again, the good people at TI Inspire have given us a way of doing it that says binomial CDF, cumulative distance or density frequency or density function, allows us to figure out the probability of success. So we want the probability of success is 0.537. My lower bound I want to be 94. My upper bound, technically it's infinity. So I'm going to just do 9. It really doesn't matter, just as long as you go to 161, because this is a binomial. Is you can either have a win or a loss. There's no like a quarter of a win, so it's a discrete frequency distribution. So you can see that if we wanted at least 94 wins, there's only about a 13.3% chance with the win rates that my team had that if we kept doing it, that is what we would get. Now, a couple of other little things that I just got to clean up as we do this. Whenever we are talking about a probability distribution, we always have to define it. And the way that we define a binomial distribution is it's always going to be x such that x is distributed binomially, and then we're going to have the number of events and the probability of success. So this distribution that we've been working with would be x is distributed binomially, 161 games, 0.537. So we just need to make sure that we are writing these things down whenever we go to use our calculator, because this shows the examiner that I know what I'm doing. I recognize this is binomial probability, and I'm going to go ahead and do it that way. So I need you to take this information, to take the snippets from the Hayes book, and to do the first 2 exercises from there. The first one is without a calculator, where you're doing some expanding. The next one, you're just plugging and chugging with your calculator, working through some applications problems. If you do that, this will make sense, and when I get back, we can kind of refine it a little bit and look at the next bits. All right, have a good one.